Aaron, I need your long arms. You can take rays of light, which travel in straight lines, from one end of the sun at the bottom toward the moon, and then project that line onto the earth. And then from that same place on the sun, on the opposite limb of the moon, boom, and do that for the other side as well. Boom, boom, right? And so you get this penumbra, which is the lighter colored shadow, okay? And then you got the moon, and then the darkest, deepest part of that shadow is called the umbra. And in order to have a total solar eclipse, you need to be inside of that umbra. The umbra typically, for most solar eclipses that are not near the poles and whatnot, will be about anywhere from 100 to 200 miles wide. And so it depends on the particular eclipse circumstances, the location in which you can be. And then not only is it 100 to 200 miles wide, it typically goes for many, many thousands of miles. So you have ample opportunity to get in the path of this umbral shadow. We don't have to go anywhere. It's amazing. Yeah.
And that, just as a clarification, anywhere within that larger circle of the penumbra will be the origin of a partial solar eclipse, since the sunlight will just barely eclipse the moon. So you'll still see the sun through glasses, the solar glasses that we use. But yeah, partial solar eclipse in that.
So for our solar eclipse, don't drive like 30 or 40 miles west, because then you'll be in the penumbra and you won't get a total solar eclipse. Okay, just stay here. Come to the observatory, please. It'll be fun. We have free solar glasses. We have music. We have 5 food trucks. We have porta potties. We have solar telescopes. We have equations. Yeah, Forrest loves this. Okay, Isaac Newton. By the way, do we all know Isaac Newton? One of the first physicists to publicly execute people. He was master of the mint, and he was the one that figured out that you should probably make the edges of your coins ridged so no one can clip the coins and counterfeit the money. And so he invented that, and then he caught all the people counterfeiting money over there in England, and then he had them publicly hanged for their crime. I thought that was kind of interesting. I'm not going to execute anybody, I promise.
Unrelated to that, he was terrible at the stock market.
This is true. Absolutely horrible. He understood all these equations, and the man invented calculus before he was 23. If you ever feel like you've accomplished something, just think about Newton, and then you're like, yeah. Okay, so how do we start predicting eclipses? The first thing to go to is Newton, and you can do everything in the solar system, like send out satellites, do whatever you want to do with Newton's laws. And Newton's laws of motion predict the following. You have the acceleration of an object is just dependent on the forces on that object and the mass of that object. So if you have a higher force on an object of a certain mass, it'll have a certain acceleration. If you double the mass of that auditory feedback, if you double the mass of that object, give it the same force, it will accelerate at half the rate. So the net force divided by the mass is this acceleration. Now, in three-dimensional space, we have to worry about three-dimensional things. And then there are 3 objects that we're concerned about mainly for eclipses. So the main objects, what are they for total solar eclipses? Sun, moon, earth, right? Okay, so would there be a way, perhaps, to calculate the acceleration of the sun, moon, and earth based on gravitational forces that they feel from the other objects? Well, yeah, and those are those 3 equations in a row. The first equation tells you the force on the moon due to the gravitational force of the moon on the earth added to the, well, subtracted because there's a negative sign. Don't worry about the math. Added to the force of the moon on the sun, okay? And then you go to the earth and you're like, wait a minute, the earth is being affected by the moon. And so there's a force from the moon on the earth. That's that first term. And then on the right, the force due to the sun on the earth. Like, okay. And then go down to the sun. Well, the sun's feeling forces too. Like, well, there's the force on the sun due to the earth, and there's the force on the moon due to the sun. It's like all these forces going on. And well, what you need to do is an easy thing, really. Aaron and I have done it plenty of times. Just solve those equations. Duh. Exactly. You would put them in a matrix. All right. Jonah is obviously upset over my equations. He's crying back there. I love you, buddy. I'll teach him later. He should know the calculus by the time he's 7. Okay, so what do you need to do to predict an eclipse? Well, the one thing you need to know is what are the forces on these objects? If you knew those, you might be able to predict where they might be in the next moment or in the next 1,000 years. And then you could go ahead and say, hey, the geometry is right. We know exactly where these things are. Then we can predict an eclipse. Any comments? Nice. He said I nailed it. Let that be for the record. All right. It is on. All right. How to predict an eclipse? Well, Friedrich Bessel did what? I left him hanging on purpose. This is one of the more complicated diagrams in the talk.
All right. So instead of we can have a change of reference frame. Let's actually go to the center of the Earth reference frame. So instead of trying to figure out the position of the sun, Earth, moon system from some arbitrary place, let's focus in on Earth where it really matters, and then have a plane dissect the Earth right through the center. So we have our X and Y coordinate running along the pole and across the equator, perpendicular to the sun. Let's figure out where our umbra and penumbra is going to be within that plane, and then just project that onto a sphere with the radius of the Earth, accounting for small deviations in the actual shape of the Earth because it's not actually a sphere, but close enough for our purposes here.
It's an oblate spheroid.
Indeed.
Okay, so if you can just do that, I mean, come on, how easy is that, right? How come the Greeks couldn't do this, right? Nor calculus. Yes, they should have known better. How dare they? Okay, so assuming you can do all that, what are what we call now the Besselian elements? Friedrich Bessel invented this method back in the 1800s. What do we need? Well, we need the XY position of the center of the darkest part of that shadow on this fundamental plane. I'll remind you, the fundamental plane is that red XY axis going through the center of the Earth. Okay, so you just need to know where that shadow, the deepest, darkest part of that shadow is hitting. Well, that's a good thing to know for an eclipse. Then you need the radius of said umbra and penumbra. Okay, you need to know how big relative to where the moon has been or is, if that shadow is bigger or smaller, so then you can know exactly the width of the path of totality. And then you need to know the angle between the penumbral cone and the shadow axis pointing directly toward the sun, and the angle between the umbral cone and the shadow axis pointing toward the sun. You need to know all these things, exactly that, plus one more thing, which is extend that shadow all the way out into space and see the point on the sky projected onto the celestial coordinate system of where that shadow is exactly lined up. Because if you know all that, you know the position of the sun, well, wherever that shadow is being projected onto the sky, if the sun crosses that point, total solar eclipse. All right, so what they actually do in practice is they take those equations, they redo everything to be centered on the Earth, they solve for the motion of all these objects, calculate these elements at a few places along those the path of the shadow of totality, and then they just interpolate to find the full solution. And that's the maps that you see of the shadow going across the land. All right. It's easy, really. I'm kidding. It's not. There's like one dude at NASA that kept doing it for years, Fred Espenak. I stole a lot of my slides, images from him. I gave him credit, though. But wait, there's more. So you got to project this path of the penumbral and umbral cone across the Earth's surface. Then you can figure out where you are. But did you know, what is the rotation rate of the Earth? 24 hours. I don't want to you on the spot, but that is a mean solar day. That is, look at the sun, wait exactly 24 hours, it's in the same spot, basically. That's what we call the mean solar day. The actual rotation rate of the Earth is 23 hours, 56 minutes, 4.091 seconds. Well, we know it down to like 9 decimal places because we're very accurate in determining these things. That's not a constant. Every time there's an earthquake on the Earth, like the other day, it changes the rotation rate of the entire Earth by distributing the mass of the Earth in a slightly different way. Every time you move around, we just change the rotation rate of the Earth by a very, very small amount in that instance, but we did.
Every time a plane takes off and lands,
Yes.
it changes it ever so slightly.
Exactly. So we have to remember about that in our calculation. This is really hard stuff because if you forgot that the rotation rate of the Earth was not constant, then, well, you would predict that, hey, instead of us getting the total solar eclipse, it would have been somewhere in Louisiana or something. It's like, that's a big difference, right? So you need to know those type of things. Ooh, don't forget about the libration of the moon. Has anyone ever forgotten about that? What's the libration of the moon? We have a demonstration with basketballs. Yes. You want to do? Okay.
We said that the moon was tidally locked to Earth, but it also rotates ever so slightly as it goes around. Remember that first picture several slides back, where there might be, when the moon rotates around the Earth, it takes a little bit more to go around, and there's a different angle and height in there. So you see a little bit of the bottom at some point, you see a little bit of the top at some point. There might be a couple days based off how you define a month. So there's a little bit of wobble as you face the moon. Even though it is tidally locked, there's a little bit of a wobble if you stare at it over the course of many months.
Yeah. Well, the side-to-side motion actually comes from torques from the sun exerting its influence on the moon's position. So the libration of the moon just proves or shows us that we can actually see about 59% of the moon's surface over the course of a year. So that affects all the calculations. Many, many other things, which I didn't even mention, extremely brief history, that will affect the positions of all these things. So one thing that I forgot to mention is that going back to those three equations that we saw, like we had the force between the Earth, Moon, and Sun, right? And all those different calculations to do. It's like, well, what is the other major body in the solar system? Well, we have a huge planet. It's named Jupiter, about 300 times the mass of the Earth, and it's only 5 times the Earth-Sun distance from the Sun. And so that is actually one of the major gravitational influences in the solar system. And so if you did not take into account the orbit of Jupiter and where it is and how it affects all the planets, and in particular the Moon and the Earth, then you would also be off in all of your predictions, and then you would be executed like those Chinese fellas. You don't want to mess up in this field. They say, publish or perish. They really mean it. Okay, so here's another excellent diagram showing this angle of inclination of the moon relative to the ecliptic plane. And so we have colored, well, not we, Stephen Wolfram, who's a turbo genius, invented the mathematical language called Mathematica. It's a programming language. Anyway, he produced this diagram for us. I took it from him. Thanks, Stephen. And anyway, he color-coded these moons at the moon at various positions around the Earth. The red is that ecliptic plane slicing the Earth and Sun in half. And so the moon either goes above that or below that, depending on the time of the month. And anytime there's a new moon getting close to that ecliptic plane, it's going to be a little bit more red in this diagram, indicating there's a high likelihood that there will be a total solar eclipse or any type of solar eclipse at that time. Because if there's a new moon right when it's crossing that ecliptic plane, that means it's exactly in line with the sun. And so that would give you a high probability of one of those.
Naturally, that makes intuitive sense. If, for example, the new moon was, say, 90 degrees to that intersection of the planes.
So one of the gray points instead.
One of the gray points. Your shadow would go significantly below or significantly above the Earth, totally missing the opportunity for any sort of eclipse.
Yeah, so there's many things to think about in the prediction of said eclipses, which is why it took people many, many, many millennia to figure out. So anyway, there's a quote from Fred Espenak, who was the premier eclipse predictor at NASA for a long time. If new moon, I think I misquoted that. If a new moon takes place within about 17 degrees of a node, the node is the location where the plane of the orbital axis or orbital plane of the moon intersects the ecliptic plane. If that occurs, then a solar eclipse will be visible from some location. So, well, we're not some location, we're Keene, Texas. How could it be that we're going to get exactly one? Yeah. Well, there's some more math. There's a thing called Saros cycles. This is pretty interesting. So if you calculate forward all these different solar eclipses, which we didn't give you every single detail of this. It's extremely complicated. In doing the research for this talk, we both figured out that we're big dummies. We don't know anything about this stuff, comparatively speaking.
So much to know.
Yeah. So, I mean, I studied black holes. I thought, oh, man, this is going to be easy. It ain't easy. All right. So there's interesting cycles to this whole thing. And these are the things that people figured out a long time ago without truly knowing what was going on. So one thing you can do is say, define the length of the year on the moon, which is a month to us, right? Relative to the stars. It's called a sidereal year, okay? Or sidereal month, however you might want to call that. Okay, it's a year to the moon. It's a month, as we call it, whatever. That's 27.3 days. It's how long it takes the moon to get back to the same location in its orbit, such that it looked at the exact same sky, right? Night sky. Okay, if you do that, it's 27.3 days. That is not on this list. There's also the synodic month that has to do with the phases of the moon. So if you go from new moon all the way around and get to new moon again, well, the Earth has revolved around the sun slightly. And so it takes an extra 2 days from that 27.3 days to get back to a new moon. Okay, and so that's called a synodic month. It's 29 and a half days approximately. Okay, then there's the anomalistic month, which is perigee to perigee. What's that? Well, if you are the peri, close, G meaning geo, Earth, if you are the closest point to the Earth in your elliptical orbit, that is the perigee. And if you define the month that way, it happens to be 27 and a half days. Well, that's interesting. These things can shift. They're not exactly perfect ellipses perfectly every time, always lined up exactly in the way that we think. It's very, very interesting. And then there's a draconic month, which is node to node. So if you go from one of those nodes, we were talking about how that it intersects the ecliptic plane, all the way around to the other node and then all the way back, that actually turns out to be slightly less than the 27.3 day sidereal period of the moon. And the reason for that is that the node westwardly drifts by 19 degrees per year. If you do that and then combine all those different frequencies, we might call them, and figure out when they might coalesce one more time and be exactly in the same position, it happens to be every 18 years, 11 days, 8 hours, approximately. And that works out to 223 synodic months, 239 anomalistic months, and 242 draconic months. Very interesting, 6,585 days. Oof.
Fascinating still is that the ancient peoples of the British Isles that I studied, whose stone circles I studied, were aware of this 18-year cycle. They noticed as the moon set over the course of many years, it would set at one position on the horizon and it would migrate north or south, and then it would go back south again and north and south. But every 18 years, there was a maximum in that oscillation that they now call today lunastices, like solstice, but for the moon. It's a lunar solstice where it's the maximum at one angle across its trajectory of setting. And some of the ancient circles in the British Isles have aligned themselves to that lunar solstice.
Amazing. So people are very good at recognizing patterns. That's why we will always be better than the AI. Okay. I'll give another talk on that soon. Okay. So this figure shows part of one of the Saros cycles. So if you notice on this diagram, pick out on the left, July 11th, 1991. There was a total solar eclipse. If you were on the big island of Hawaii, you could see it. We actually lived in Oahu at the time. My dad was in the Air Force. We lived at Hickam Air Force Base. And I remember them saying back then, I was 5, I remember them saying, we don't have any solar glasses, you can't look at it. But I think I remember it getting dark. That could just be my mind playing tricks on me. But if that is real, and I do actually remember that from when I was 5, that would be my first partial solar eclipse. We were at like 99%. If we had only been on the big island, then we would have seen 100%, and we would have seen totality. That would have been cool. But anyway, if you calculate all of the eclipses for that particular Saros cycle, you'll notice the next one to the right was up and above all the way in China, July 22nd, 2009, all the way top right. Okay, So that's exactly 18 years. What is it, 11 months? Or 18 years, 11 days, 8 hours. The 8 hours, if you look at the US on there and then China, they're like, well, they're about 8 hours different on the planet. So that's why it's all the way back over there. And then the very next one in that cycle will look like August 2nd, 2027, going through Northern Africa and Egypt and that kind of thing. Okay, very interesting. And then the next big solar eclipse that's going to happen in America is one of the other eclipses in this cycle, the Saros 136 cycle, which is August 12th, 2045. So if you look at that one's going to be amazing. I hope you're around for it. It will clip the panhandle of Texas by like 10 miles. So if you're up there on someone's farm, you can do it and you can see it. But we have already been planning this out. It's going to be in 21 years, but I think we're going to be in northern Nevada in the middle of the dry, arid, high desert. There's going to be no clouds ever. It's going to be awesome. Anyway, right there, we'll probably get approximately 5.5 minutes of totality. So look forward to that one in 21 years. I told my students the other day in astronomy class, guess what? In 21 years, you're going to be older than I am currently. Welcome to my nightmare. You can't stop it. You just get older. Question for the audience. No. Of course I can. Yeah, this one?
Yeah, wasn't there one, my dad said that there was one in the 1970s?
Yes. So that was a part of a different Saros cycle. So this is not all the eclipses that were happening. There are a bunch of different cycles, yeah.
They're not going to go in order. They kind of like interweave with each other.
Yep.
If we were to plot them all the cycles, it would just be a whole mess.
Yep. Yeah, so the point of the Saros cycles is that they will look very similar in shape and curvature as projected onto the surface of the Earth. And then they're just going to be separated by, a third of the planet, the 8 hours difference, in addition to the 18 years, 11 days.
And this is just one small segment of one cycle. The cycles last like 1,000 years?
Usually the cycles last about 1,000 years. There's about 80, on average, eclipses during one single Saros cycle.
So it'll start at the southern hemisphere or the northern hemisphere at the poles, and it'll migrate either north or south, east to west?
Well, west to east, yeah.
Okay.
So, yep.
And then when that pattern finally goes off of the surface of the Earth and is now in space, you no longer have an eclipse, and then you start a new cycle.
No, you're right, east to west, yeah. Or west to east, whatever you said, yeah. Well, question for the audience, because, that's a lot of math, right, and thinking. All right, moving on. We have a story to tell. We were there, and you will be here for the August 8th, but we were there, April 8th. We were there for the August 21st, 2017 total solar eclipse. If you were in Keene at the time, it was partial. Boo-hoo, sorry. We traveled to the middle of Wyoming in a little place called Shoshone, and we actually went to a little reservoir a little bit west of Shoshone called Poison Creek Reservoir. It's the worst name for a reservoir I've ever heard in my life. And we were there like a mile off the main road at this tiny little campground right on this reservoir. And we knew going into it that there would probably be no clouds, middle of Wyoming in August. I mean, come on, right? And so we were there, and my wife was there. This was prior to us having kids. And our good friend Aaron here was there. It was amazing. And my parents were there, and we had a couple other friends and family show up. And we went over there, and in the morning drive from where we were staying, which was a little bit north, to where we had to be in the exact kind of almost center of the path, I was driving, and then, or were you driving?
I think we were both driving in separate cars.
Yeah.
I was following you.
And then who did the deed? Who hit the bird?
It was you.
I hit the bird? My memory is not so great. I hit a bird. That poor bird never got to see the eclipse. On accident, I'm sorry. It was a little sparrow. Fly away, little sparrow. I didn't know if I wanted to tell that story, but I thought about it just now. I had to tell it. I promised not to kill any birds this time.
The bird really flew into him.
It was his fault, really. But relativity tells us who's right there. The frame of reference of the bird intersecting with my frame of reference, or my, I don't know. Sorry, bird. Anyway, we were there, and we get out there, and we're waiting for hours and hours, just talking, and we were just very excited. How's that? This whole thing, even though it's mathematical, all these wonderful things about the universe that you might have to know to predict these things, it's a personal thing. You'll never forget your very first total solar eclipse, or your second, I hope, or your third or fourth or fifth, whatever. What I'm hoping to convey here is that even though it's kind of a nerdy thing, it's more of a personal thing. You get to be connected to the universe in which God created in this way that you will never experience in any other way. Because what you're going to see during that totality is that the bright sun, which has been bright your whole life, is now going to be a black hole on the sky. And you're going to freak out, and you're probably going to hoot and holler, because I know you people. And you're going to be like, ah! It's going to be awesome. I'm getting goosebumps remembering when it happened to us. And what you're going to do is you're going to look at that thing, and then you're going to quickly realize your place in this universe, which is, here I am on the earth, and connected to the sun and moon is this ecliptic plane, and the moon has just crossed it at the right moment, at the right time, and we're on the right moment at the right time on earth to see that happen. And then we saw Venus during the day, and then we saw Regulus, the brightest star in the constellation Leo, and we were just amazed, and we turned around, and there was a 360 sunset everywhere you look. It was just amazing. And what else can I say about that? Well, we had 2 minutes and 20 seconds of totality, and it went by like that. Oof. It was nice, though. And, well, this time we get 3 minutes and 43 seconds here. Okay? So, just enjoy it. The maximum amount of eclipse you could possibly get, by the way, theoretically, is 7.5 minutes. So you're getting a pretty good one here. And I hope that you think about these things. So we'll talk a little bit more about that. But during the August 12th or 21st, 2017 eclipse, it was an amazing moment for me personally as an astronomer, because I got interested in astronomy in 1997. There was a comet, Hale-Bopp. If all you more seasoned individuals in the crowd would remember that you could see that thing even from the brightest cities. That thing was an amazing comet. It was in March of 1997, so I was just about to turn 11 years old. And I got to see that thing through my grandpa's binoculars, and I was like, ooh, crisp, clean, nice comet. I love that. I want to study that. And then I was like, what's beyond the comets? Solar system, what's beyond that? Galaxy, what's beyond that? Other galaxies, what's beyond that? The whole universe, ooh, what's inside there? Oh, is that a black hole? I want to study that. So anyway, that got me my whole career of my life. The reason I'm even here was that comet. It was silly, it was crazy. And then I got this book right around the same time, a book on astronomy. It's amazing. I have it at my office. I can show anybody. And I flipped to the back. Appendix, table of solar eclipses. Oh, wow, they can predict those things that far in advance? Oh, when's the next one in America? Oh, August 21st, 2017. In 19 more years? I better start planning that. I don't want to miss it. And anyway, I've been thinking about that one ever since. And that moment when totality began, it was just this upwelling of emotion that I thought, this is the coolest thing I've ever experienced. There's this three-dimensional aspect to the solar system that you just can't experience any other way, unless maybe if you go to space. But I'm already spaced out, so maybe Aaron can tell his part of the story there. So,
yeah, my interest in solar eclipses has not been as thorough as Jared's, but I'm sure when I first met him, the conversation went something like, "Hi, I'm Jared. What are you doing in August 21st, 2017?"
Correct.
Back in like 2009. That's probably one of the first things he said to me.
Please join me.
Yeah. So yeah, early on when Jared met me, we were already making plans to go to this particular event, and I was all for it. I'd never seen it before, so yeah, let's go for it. And I was racing myself to finish grad school before I got to that event, because I thought it'd be cool to see it as a doctor. And luckily I graduated in May, a couple months before the eclipse. Jared and I drove down to the middle of nowhere, Wyoming. I can't stress that enough. It is the middle of nowhere. We were trying to get as close to the center line as we possibly could. And we got there, and there's a small campsite. There's a couple people hanging around. And so he and I, being natural teachers, are teaching things about the eclipse to people we just see at the campsite. And behind us, I hear a voice say to us, "I recognize those voices." And I turn around, and it's my grad school advisor in the middle of nowhere.
Amazing.
The odds of that happening still blow my mind to this day. So they truly do bring people together in a weird way.
Absolutely.
I have no idea what he was doing there. How did he even find us in the middle of nowhere?
Is he going to be here?
Part of me is wondering, like, is he in Texas right now?
I'm thinking about, like, if he went to a conference in DFW somewhere in that area, and then he's like, hey, I'm looking up on Google Maps, observatory near me, and he saw Thompson Observatory as #1 result. Ooh, I'm going to head down there. I think he's going to be here. I'm just going to say. Okay, anyway. Is that?
Yeah, that's it.
All right, so what to expect on Monday in like 36 hours. So here's that path of the shadow. It's right through us. Oh, man, that's amazing. We don't have to travel at all. And so we are over there. Well, you know where we are. And we're slightly off the center axis. That's fine. If you were on the center axis, you'd get about 4.5 minutes of totality. We get 3 minutes and 43 seconds. But if you're outside of that, please don't travel anywhere on Monday. If you're outside of that, you will not see it. Okay? Very cool colors on that one. All right. Now, this is the part where if you want to take a good picture and remember these times, these are the exact times for everything that's going to happen at the Thompson Observatory on Monday. So if you go anywhere else, these times will vary, and you would have to look it up or talk to me. I can help you out with that, figuring out where you need to be, but at what time. But the first contact, that's what we call when the moon just starts clipping the edge of the sun in terms of its coverage. That's going to be at 12:20:51 p.m. Central Daylight Time. So if you're there at 12:20, start looking through our scopes. You'll start seeing the moon take out a chunk of the sun. It's pretty cool. In yellow is second contact, the most important time of a total solar eclipse. That's the point where the moon now completely covers the sun. At that time, it is 1:39:20 p.m.
That's when all the hooping and hollering starts.
Yeah, you're going to freak out, I promise. Don't blame me, okay? I didn't do it. The next 3 minutes and 43 seconds are going to be the greatest moments of your life outside of your marriage and your kids and that one time that you made a basketball hoop happen thing. I used to be good at basketball. Now I don't even know how to talk about it. Okay, so third contact is when the moon now starts sliding off the face of the sun. It's like, oh, no, it's over. Ugh. Very anxious moment. But you got to experience that 3 minutes 43, so you should be happy and excited. Amazing. And then if you want to stick around, nobody usually does. The very, very end of the eclipse is 3:01 p.m. So if you want to take a picture of that, those are the exact times for the Thompson Observatory, or more or less anywhere in Keene. They might vary by 1/10 of a second anywhere else in Keene. But if you travel anywhere else, you'd have to recalculate. So those are the exact times.
Just to add to that, the yellow lines are where you can take your glasses off. The white ones where your solar glasses.
Yeah. So we'll be giving away solar glasses for free at the observatory. So if you have your solar glasses on during the time, those yellow times, that 3 minutes, 43 seconds, you will see nothing. You get nothing. You lose. You don't even get the right to see the next one in 2044. We're just going to make fun of you. Don't worry. No one will let you do that. Okay, so if you see anyone wearing those glasses during totality, rip them off of their face. I promise you it'll be worth it. They'll get mad at you for a second, but then they'll be like, "Ooh, wow." So, all right, this is the coolest part. Well, I don't know. All of this is cool to me, but this is the coolest part. Last time during that August 21st, 2017 total solar eclipse, and I know this should have been bigger on the screen, what we saw was Venus. That was the other planet we could see, and we saw a bright star Regulus in the constellation Leo. During this particular event on Monday, right in the middle there, kind of, lower right of middle, is the moon and the sun, right during totality. All the way over to the right, and those little blue letters, I know you can't see it, that is Mars and Saturn, separated by a few degrees on the sky. A little bit more between Mars and Saturn and the moon and sun, we've got Venus. Venus is the brightest star or brightest planet in the sky, be very bright. And then along that same ecliptic plane, which is that purple line, You keep going up and to the left of the sun will be Mercury. I don't know exactly how bright Mercury will be, but we might be able to see it. And then all the way a little bit more over to the left will be Jupiter. There's a little symbol to the right of Jupiter indicating a comet. There's a comet currently called Comet 12P Pons-Brooks that has a period of 71 years. So if you don't see it now, you wait for another 71 years. If it brightens up a little bit more in the next 36 hours or so, we'll be able to see that with our naked eye during the eclipse. But most likely you won't see that. And so don't look for it. Look at the moon and the sun. But if you're really interested in getting that three-dimensional aspect to the solar system that you've never seen before, seeing every planet in this exact line of the ecliptic plane is just amazing. So we get to see 6 planets. Yeah? Mars, Saturn, Venus, Mercury, Jupiter. An astrophysicist that doesn't know how to count, well, don't forget your favorite planet. You're standing on it, okay? This should be everybody's favorite planet, by the way. I get that question all the time. What's your favorite planet? Well, can you live on any others? You're welcome. Okay, there are nerds out there there are scientists out there that predict the exact shape of the corona of the sun during the next eclipse. They've done this through numerical modeling of magnetohydrodynamical aspects of the corona of the sun, blah, blah, blah. Okay, cool. That's what it might look like to our eye. It'll be very, very cool. So there's a lot of things going on there, but the main thing you want to look out for is how far that atmosphere of the sun, that's the outer atmosphere of the sun, extends away from the moon. It's really, really neat. It looks way better than that in person. And then right around the limb of the moon, so that circular edge, there's going to be a bunch of reddish pink things. Well, what are those? They're going to be prominences. These are regions of plasma being ripped off the surface of the sun, being supported by the extreme magnetic field of the sun. They're just going to be chilling there on the edge, and you're going to see them bright reddish pink from the hydrogen alpha emission of that prominence. So that'll be cool. In addition to all the planets and all that stuff.
The corona being blue, I believe, is from ionized iron. Is that correct?
Correct.
Highly ionized iron, so ionized that you can't even create it on Earth. It's so hot. It can only be formed in the corona of the sun.
The corona is 2 million degrees. Very, very hot. It's the hottest thing you'll ever let your eyes gaze upon, besides your wife or husband, whoever you are. I didn't want to get in trouble. Okay, what to look for prior to and after totality. So not during the total phase. What are we going to look for? We're going to look through our solar glasses at the sun. That's kind of cool, you know. You get to stare at the sun safely. We have all the ISO certified glasses. You want to go next? Or I'll keep going.
Keep going.
Okay, look, we're going to look at the sun through properly filtered telescopes. We have many telescopes that will be outside at the observatory staring directly at the sun. Oh no, we got them properly filtered, so it's going to be amazing.
So I'm taking this
one. You take that one.
Yeah, the evolution
all right, fine.
This one fascinates me. When the eclipse starts to happen, when the moon starts blocking out the sun, I want you to do a couple things. If you're standing under a tree, look at the shadows of the leaves. If you're not standing under a tree, I want you to make a pinhole with your fingers. Just press your fingers together and make a little tiny hole and look at the shadow of that. What you will see is a replica of what you see in the sky, but you don't need your glasses when you're looking at the shadow of it. You will see crescents of the sun repeated in the shadow. It's bizarre. And when you're under a tree, you'll see thousands of them on the ground. You'll also see distortions of your fingertips. If you hold your hand out like this, you'll see weird like claws. Correct?
Yeah, because
like spikes because
every
the
shadow is a
of the
crescent.
sun
Yep.
as the moon passes over.
Yeah, it looked like you have claws. It'd be cool.
Yeah. When the moon starts to eclipse the sun entirely, and you see sunlight bead up, which is something else that we'll talk about.
Mm-hmm.
The light source will become what's like a pinhole of light. It's such a narrow beam of light that your shadows are going to be extremely crisp to the point where you can actually see the shadow of the hair on your arms if you look carefully.
Like on the ground. Yeah.
It'll be just an absolute crisp image of your shadow.
Yep. There's also something optically called the Purkinje effect. And this thing is your eyes detect color in a weird way when the overall light levels around you are not as bright as they might normally be. You look out on a bright day, red, green, blue all look the same as they always have. Pretty cool. When the eclipse starts happening, the sun gets blocked out by a lot. It's like there's only a tiny amount of light coming through. It's pretty dark out. Your eyes will react to those different colors in a different way. So I'm going to be in a blue polo shirt that says Thompson Observatory. And if you want to wear bright, primary colors, you're going to notice that they look differently compared to what they normally do. And that's this weird optical effect. There's probably going to be some upper level clouds. We've been looking at the weather predictions, and there's something called atmospheric optics. So when you have these upper level clouds, they're all made of ice. Sunlight comes through, bounces around those ice crystals, and perhaps then enters your eye. And depending on the geometry there, you could get these interesting solar halos or other types of atmospheric optics phenomena. So look for those. Like if there's any sort of cloudiness in the sky, you might see some rainbow coloring somewhere. That would be cool.
That pinhole nature of light going through the regions on the Earth, the moon, like the valleys of the moon, that pinhole aspect of the light might also make the rainbows tighter, or it might change.
It might change their,
shape
yeah. It'll be really interesting.
from
Yeah,
what you normally see in normal atmospheric.
we'll point it out if it happens. Okay.
Yeah.
Then we were talking about this this beating of the light right at prior to totality. That's called Bailey's beads. That's that Francis Bailey that saw these kind of and noted them for the first time. As the light of the sun passes right around the limb of the moon, that edge of the moon, it's like, well, the moon is not a perfect sphere. It's got mountains that are 10,000 feet tall on them. And well, if you were looking at a mountain range and the light's poking through, well, it could be poking through one area, but then blocked in another. So there's going to be this beating effect. Very strange. And the diamond ring effect is a very similar thing where it's almost at totality. You see this black disk and then one bright point of light, and it looks like a ring. Pretty cool. All right, what to look for during totality. This is the cool part, and we kind of talked about it already, but here we go. We got the corona of the sun, the hottest thing you'll ever see. 2 million degrees. Hotter than Texas in the summer. Okay, then we'll see the solar prominences. I talked about those little pink emissions that you'd see along the limb. And then we'll see those planets. We'll see other stars. Orion will be rising. You'll probably see Orion. And potentially that comet, but probably not. It's probably going to be too dim. There's something called shadow bands. So this is the effect of this tiny sliver of light piercing through the turbulent atmosphere of the Earth. It's going to, about a minute prior to and a minute after totality, there's going to be these like snaky wave features on the ground if you have something bright on the ground. So I think we're going to bring a sheet, and then you can see that, or project it on the side of the building, something like that.
Or if there's a sidewalk or a white, like a parking lot or something, look at that. Don't look at the grass. The grass is too fuzzy and distorted. You won't really see it there. So flat and like a very neutral, bright color. Yes. Yep.
We talked about the atmospheric optics phenomenon. Potentially, we'll point that out if it happens. And then we talked about that 360 sunset or sunrise. It'll get about as dark as maybe half an hour after sunset. Okay, so you imagine going out tonight, half hour after sunset. Think about how dark it is. That'll be about as dark as it gets. It'll be real cool. Unless it's real cloudy, it'll get much darker.
If you took a picture of the horizon during a total solar eclipse, you would be convinced that the sun has actually set. But it would look like that anywhere you look.
But way off in the distance, if you can see the entire horizon, bands of orange, because those are the parts of the Earth that are still not in the shadow. You'll be able to see that. That'll be cool. And then it's a whole body experience. You want to listen too. The birds are going to freak out. So are the insects, because some birds and some insects are nocturnal versus not. The things that are normally awake will think that it's getting dark and they'll go to bed. And then things that are normally asleep during the day, they're like, hey, it's kind of dark. I'm going to go eat. And they're going to wake up. So it might be that we hear a bunch of insects and then all of a sudden they just shut up. So that'll be cool. What else do we have on here? That is the final slide. We should have had thank you for your space time. I want to open it up to questions. I know we went probably way over time, a little bit over time, but let's, if anyone wants to ask a question, Maybe someone could run a microphone, or maybe I will. I don't know. Can I come down here into the audience? Will you let me? Yeah, what's your question?
Yeah, just was wondering about the solar glasses. Those are only once the eclipse starts? I've never used solar glasses. So, or can you use those anytime?
So you can use them anytime. The recommendation on the actual solar glasses that you throw them away after 3 years. They might get a little bit degraded or something like that. But anytime you want to go look at the sun, if there's a cool sunspot on the sun, you bring those out, look up. It's awesome. So the sun is about the same size on the sky as the moon, so you'll be able to see this bright orange ball. And yeah. Another question? So the solar glasses will be handed out for free, by the way, at the observatory. We got like 3,000 of them, so.
So how badly do you think the clouds may affect how it will look here?
Well, yeah, I'm no weatherman. However, the thing is, people run these numerical weather models all the time, and there are different ones. There's ones that are run on supercomputers in America, and there's ones that are run on supercomputers in Canada and elsewhere. And typically, a couple days in advance of any date, those numerical models will show a convergence. And if that's the case, then probably they're all agreeing that's probably what the weather's going to be. Right now, they're showing high-level clouds, which may or may not be too dense to see through. Hopefully not. And a potential for those low-level clouds. Now, every time I look, it's a little bit different. So I think we're just going to get lucky, I think. I think that if we have all y'all praying for it, we're going to be good. Okay, so please continue to do so, or if you haven't started, start. But you never know. Sometimes they predict extreme, severe weather events, and they never pass here in Texas. And sometimes they'll predict perfectly sunny skies, and it won't be. So, yeah. Another question?
When you were talking about the calculations for predicting a solar eclipse, and you mentioned Jupiter, what about the planet Mars or the asteroid belt?
Yeah, so every planet technically matters just a little bit, but Jupiter is by far the most massive, but beyond the sun, most massive object in the solar system that will affect things. Yeah. So many questions. Who's next?
How do people know when the solar eclipse is going to happen or end?
Yeah, so it's all those calculations. It's crazy. You think, man, this might be easy. We just think, okay, there's an orbit of the moon and an orbit of the sun. Well, when they line up or something, but it's really a highly technical mathematical thing, and you have to take into account the non-constant rotation rate of the Earth, and you have to know exactly where you are relative to everything, and the moon and sun have to be exactly lined up. It's crazy. And so there are only a couple people in the world that really do this at the expert level, and I don't know, does that answer your question? Awesome.
There's a question.
We can talk more about that later.
There's a question in the very back.
Very back. I like running the microphone. It's fun. You get a workout. Yeah.
Yeah, I just had a question and a concern regarding the solar glasses during, what do you call it? When the whole thing's covered, total. Yeah, I just heard an ophthalmologist on TV yesterday saying that there's still quite a bit of light coming out, and he said to wear them the whole time, but that's just what I heard. Okay.
Well, that's unfortunate because during the actual totality, if you wear those glasses, you will see nothing. And I guess the danger becomes when you're trying to look at it right as it starts, and those little bright peaks of light going through the mountains on the moon might, enter your eye or whatever. It's like, well, you've accidentally stared at the sun before. It doesn't hurt anything more than that. I'm not suggesting that you should purposely do that, but if you wear the eclipse glasses during totality, you will see nothing. It'll be very disappointing. So, yeah. So you'll know. We'll say on the PA system when to take them off and whatnot.
You mentioned, you showed us with your diagram how the moon circles in a month the Earth. And so I'm wondering, is the moon crossing the elliptical plane this time heading in a upward northward way across the plain, because I see that the path is curving northward.
Right. I would believe so. Yeah, that would be called the ascending node. So yes, I think so.
Ascending node
I would
is
have
the
to look
word.
that up in detail, but I believe that would be the case. Yes, because if you have the sun and moon going up like that, then the shadow will follow like that. Yeah, I think that's right. Yeah.
So could you briefly explain again why it has to be a new moon for a total solar eclipse, and why should that matter to a Christian?
Well, I love the softball and then the hardball right after. So the new moon has to be a new moon because, well, you think about it, right? You're like, all right, well, here's the sun. The moon, if you haven't noticed, you need to go out and look at this, like today. I guess it's cloudy though. But if you go look right now, the moon is slightly westward of the sun. Tomorrow, Sunday, it's going to be about 15 degrees closer, and it's going to be slightly less of a crescent moon. It'll be towards new. And then right when it crosses, you're seeing the entire backside of the shadow. So if you were to go on the far side of the moon, it's in complete brightness. It's noon on the far side of the moon. On this side, it's midnight. So you're just seeing that dark side. And so I've thought a lot about the eclipses and what that means relative to people who might believe in God and say, okay, what does this mean to us? You know, God created this whole nonsense. And I use that in the best possible sense. It's like, why? Why did he allow us to see this, right? In my opinion, I think it's to believe and know more about him and his love. You know, he created that for us. We got to see it. We get to experience it. If we're lucky enough to be in the path, by all means, let's do it. Does it mean anything more than that? Probably to every person in this room, it's going to mean something slightly different. But for me, it's just furthering that connection I have to this creation. It's like there's no other way to view that particular aspect of that. Maybe if you went to space or something, but yeah, to me, it's just that. Nothing else. Yeah. More questions?
Two questions. One is, what is the width of the shadow on the earth when totality? And then the second question is, what has been your favorite conspiracy theory about the eclipse?
Do you have another 3 hours? No. So I think during this one, the path width is something like 120 miles. I could be wrong about that. Something like that. And typically they'll range from very, very thin, maybe 10, 20 miles to well over 250 miles, 300 miles, something like that. So it depends, especially those ones that kind of intersect toward the poles. Those will be a lot wider. Of course, who's traveling to Antarctica, right? So my favorite conspiracy theory about the eclipse, yeah. How much of trouble do I want to get into? My favorite part is people ascribing meaning where meaning is not to be ascribed. They say, well, this path of totality, we're going to travel through like 12 cities named Nineveh. Okay. Those cities were named 100 years ago. Why does that matter? In Nineveh, wherever state that is, they're going to look up and they're going to see the eclipse, and then it's going to end. And then they'll be left wondering, well, why did I focus so heavily on this instead of focusing on the thing that God brought you there for, which is to experience this with your friends and family and loved ones? I don't know. I don't know if that's my favorite part. None of it's my favorite, but yeah. Anyway, yeah. So, no other questions? One more? Yep, I'll jump off the stage for you.
Yeah.
According to the internet, which is never wrong, there.
Abraham Lincoln said that.
Right. I was looking up the eclipse, or the possibility of an eclipse, where there's a big argument during Christ's crucifixion. I've heard some people say that there was, and some people say that there wasn't. Have you heard? Do you know anything about that?
Certainly not an expert on it. Yeah, certainly not an expert on it. I don't believe that they have shown in their tables, which they can predict back down to like 3000 BC, that there was one. But again, we don't know the exact dates of everything back then anyway. So it's likely that people that were around in that area had probably seen one in one of their lifetimes, and they could have been thinking about that, but I'm not sure there was one during. I'm not an expert on that, however, so I will defer that to the experts. There could, yeah. So there's lunar eclipses as well. So. Ah, right.
Possibly, it couldn't have been a solar eclipse.
Okay.
because Passover is always a full moon.
Well, if that's the case, then that would, yeah, if there was a lunar eclipse, there could have been one. Yeah, I don't know. I'd have to look into that. I haven't done any research on that, to be honest. Yeah, so, yep.
So that was a supernatural darkening of the sun when Christ was on the cross.
Just to piggyback onto that answer, our calendar has changed over the course of hundreds of years as well. Like we can back predict, I guess what would be the word for back predicting, like back calculating certain events or predicting the future, but we're basing that off of today's calendar. And there's been the Gregorian calendar, the Julius Caesar, Augustus calendar, Julius Caesar, they all have their own variation of a calendar. And that could probably affect the calculations that we have. So we might have a certain date that we call like August 21st, 50 BC or whatever, but that would be something completely different based off another calendar that they were using at the time. So.
Yeah, I was just about to say that. I mean, God doesn't need to have the moon lined up to do anything, right? So he could have darkened the skies in other ways. Like you don't have to have these special alignments of all these special things. It's like God doesn't care. He can do whatever he needs to do. So
There's
yeah.
already evidence that shows when God made the earth stop. I can't remember what book it was, but there is evidence. Joshua, yeah. There is evidence that happened.
Right. So, it's like, I'm not the expert theologian on any of this stuff. So I'll defer to my friends in the theology department, and he can probably answer all these questions. But yeah, so I'll do more research, but for sure. Yeah. Anyway, probably, I think our kids are getting a little cranky back there, so we might.
There are two announcements that I want to make. I handed out some stuff to you. There's more on the back table, but the time is a little bit off on that. It's 12:20, not 12:40, that the first contact, and the others are approximately right within a few seconds.
Yeah, those are the correct times now on the screen. So if you didn't take a picture of that earlier.
Yeah, there you go. The second is the night before the eclipse, Sunday night, tomorrow night, the observatory will be open if there's some open skies. We don't know whether there will be or not, but we'll be up there. There are people from Minnesota that wanted to have it open so they could use the telescopes there. And so we'll just go ahead and open. And then the following night after the eclipse, will be open again because there's people here from many different states already. And some of those want to see through the telescopes that we have up there. So you are welcome to come. Either of those nights will open about sundown, close around 10:30, 11 o'clock, something like that, if there's open skies. So those are available to any of you that want to come up. Otherwise, we're open first and third Friday nights every month, if the weather permits. And you are always welcome. There's no charge, and you don't have to make reservations. It's just open to general public. Last night we were open because it was the first Friday night of April, and we had about 30 people there from all different places. And one was here from Brooklyn, New York, because he's visiting in Dallas, and he said, I've never looked through a telescope before, and I wanted to see if I can get there in time so that I could look through a telescope. We get people from all different places. And this weekend in particular, a lot of people, California and other places like that. Based on that, I wanted to have two people stand up. They're in the back. These two people have watched many different eclipses. George Saxon, I believe this will be his, would you stand please? George, is this your fourth total eclipse?
This will be my fifth. I've been to four.
This will be your fifth. Now, I don't want him to be overshadowed, so to speak. So next to him is Bob. Bob is from California? No, Virginia. How many for you? 6. He has seen 6 total eclipses.
Just couldn't get over it so much, and he's been to many since then.
Yeah. So would this be your 7th? This will be your 6th. Wow, that's just absolutely amazing. And he's traveled all over to see those. Yes.
Do you have any comet viewing opportunities? Or?
We saw the comet Thursday night. He had his students there Thursday night.
Yep.
And we saw it. We did, yeah.
Yeah, we did see it.
And
Yeah.
the previous Thursday night.
Yep.
That comet is just below Jupiter. You'll see Jupiter up in here about sundown. And that comet is just below Jupiter to the right, just a little bit. When you see it through a telescope, it looks like a little fuzzy ball. You can't see the tail visually. You have to have a camera to get multiple shots to be able to see the tail. But yes, the comet is visible. It may not be dark enough to be visible for the eclipse, and it would be much higher in the sky during the eclipse time.
Yeah, I don't think we'll see it. So.
Yes.
One last question. These guys said that they've been to like 5 or 6 eclipses, and that made me realize, wait a second, there are more eclipses in the time period than less than 18 years, because there's one here, and then there's one in the Middle East in 2027. So
Right.
why can there be 2 in the same 18-year cycle, and why are there multiple ones in the same 18-year cycle?
Oh, yeah. So, the different cycles are different eclipse circumstances. So just based on the geometry, yeah. So anywhere on the world, about every year and a half or so, there's going to be a total solar eclipse. Yeah. Yep.
Remember when I said that if you would plot them all, it would just look like an absolute mess.
Oh, okay. Well, that's kind of convenient.
Yeah. So the next one in America is August 23rd, 2044 in eastern and northern Montana and North Dakota. And then beyond that is the August 12th, 2045. And that'll be a great one. So that I talked about. So if you want to just not go anywhere, just wait 21 more years. Absolutely.
All right. Let's pray, and I hope you're praying for clear skies. And people keep asking me about that. And I said the forecast for crossing the Red Sea wasn't very good either. It's all up to God. If he wants us to see that, he'll part the cloud. I think it's easier to part the clouds than it was the Red Sea. So we're going to ask for that. And thank you so much, both of you, for being here. Father, thank you for the opportunity to have an understanding of how accurate your universe is, how predictable many of the things of the universe are, and how wonderful the creation has been, and how we're being able to understand just a little part of it. Thank you for the eclipse that's coming over our town on Monday. I ask again that if it's your will, that we will be able to see the totality, that we'll be able to see the sky, and that the people who are here may be blessed because of it and may recognize the greatness that you have and the tremendous love you have for each one of us. Thank you so much. Amen. Amen. People have asked how many people are going to be at the observatory. If it's clear, the predictions were 2,000 people. If it's cloudy, may have half of that, because I've had calls, people are now traveling to Maine, Arkansas, and other places like that, because the predictions are for clouds. But we'll still have a lot of people here. We'll have food trucks up there. We do have about 10 telescopes that will have solar filters on them. So you can see the sun if, at any point, you can see the sun if it's not cloudy. So thank you very much.
Thanks, Jerry. Yep. I know. Why is this- It's tiny there. It is this weird ring. I don't know why it does that.
Were you supposed to sing during this time?
I think someone left that here and a watch. There's a watch. Yeah, right there.